All right, good evening, pre-calc people. So today we're going to take a little jump forward and we're going to talk about complex numbers. I'm gonna, I'll try to put the stuff that's important for your homework up at the front, but if you're watching these videos, well, thank you for watching the videos. But if you're just watching them for the homework, that's fine. You probably don't want to watch this video all the way through. Okay, so there's a lot of explanation because the face-to-face class I've noticed, and some of you I've noticed you're a lot more comfortable if you know why and how things work rather than just here's how it's done. So if you don't have time to watch this because you don't want to do that, that's fine. But here we go. All right. So let me go ahead and do this. Okay, get rid of that. Get rid of this. Put this up. Okay, so we're going to talk about complex numbers. Right. So try to put the stuff important to being able to do at least the first part of your homework first, and we will definitely be doing a part 2, maybe even a part 3 to go through your homework stuff, okay? So I'm going to assume that you have very little experience with complex numbers because the daytime class also had very little experience with complex numbers. So the idea here is that, well, we're going to have this equation, x squared plus 1 is equal to 0. And then we get x squared is equal to -1. And at that point, we say, we're done. There aren't any real solutions. We're you can't graph it. It's over. But we're going to force the issue. And say, you know what? We're going to keep following the algorithm, and we're just going to make it work. So we're going to say x is equal to, I'm going to use the primary square root, the principal square root, and we're going to get the square root -1. So well, that's an interesting thought. What else can we do with that? Well, first off, let's go around and start calling it I instead. Okay, so that's what imaginary means. It's not that they're actually imaginary, but you know how we have real numbers? We just want to differentiate between the real numbers we already have and this new kind of number. Let's call it imaginary. Okay. I have a friend of a friend who knew an editor or knew a mathematician. He used an editor that never had like an algebra class. So he's like, he used imaginary an awful lot. So he'd go with thesaurus, and he would replace imaginary with all sorts of other words to describe what was going on. So he had unreal numbers, he had dream numbers, he had crazy numbers, all sorts of, complex was a number that we call complex, but with difficult numbers. So it is all sorts of things, but they're just imaginary, and the reason they're imaginary is they're not real. Okay, so it's nothing special, cool, or like they're not illusionary, or they're not really not there or anything. They're used. Okay, so the form that we're going to have is an a plus bi. Okay, all of the forms we're going to use for imaginary for complex numbers are going to be a plus bi's. Okay, that's the rectangular form. We're also going to talk about the polar form. Okay, we're not there yet. We'll get there. Okay, so the idea with rectangular form is like, well, do you know? Okay, we're going to go start with I, right? That's just equal. I to the 1 is just equal to I. Okay. I squared, we're going to go back over here. We're going to say, well, wasn't I is equal to the square root of -1? Now, be extremely naive about it, but what if I square both sides? What do we get up? We get -1. That's what it is. -1. Okay. We have I cubed, which is equal to I squared times I. Right? The bases are the same. We can add the exponents. So we have I cubed is equal to I squared times I. So this is -1 times I is equal to -I. All right. And then I to the 4th power, okay, we're going to have this I squared times I squared. The terrible squared. Okay, let's get rid of all of that. Okay, so we have an I squared times I squared. Okay, so we have -1. Okay, and then that's equal to 1. Later on, when you take Calc 3, you take maybe one of your physics classes, statics classes, you're going to be writing I, J, and K a lot. You're going to be writing I and J a whole lot. So that's why my I's and J's have little serifs on them, because if I just write that, like, did you mean an I or did you mean a J? I just got tired before you finished. I'm not sure. So that's why my I's have, if you look at the little hook on a letter, right, that's called a serif. Okay. So, sans serif, that would be something like that, where it didn't have any little hooks. Okay. So serifs, that. Okay. I to the 5th power. There are all kinds of crazy things you can run in math class, right? I to the 5th power is equal to I to the 4th times I, right? Bases are the same, we add the exponents. What's I to the 4th? I to the 4th is 1 times I, that's I. Okay, so I to the 5th is equal to I. I to the 6th, okay, that's equal to I to the 4th times I squared. So it's 1 times I squared was what? It was -1. 1 times -1 is -1. So I to the 6th, -1. I to the 7th, okay, that was I to the 7th is equal to I to the 4th times I cubed, right? The bases are the same, we add the exponents. So that's 1 times, what was I cubed again? I cubed was -I. So it's -I. And then I to the 8th is equal to -1. I'm sorry, is equal to 1 times +1, right? I to the 4th times I to the 4th, that's equal to 1. So usually at this point, I'll ask students, especially face-to-face, do you notice a pattern yet? Okay, there is a pattern. So every I to the 4th power goes back to being 1. And then we just repeat this cycle. So let me show you on a real and imaginary graph. So we have, it's kind of like our Cartesian graph, right? Except we use the x-axis to be the real part of the numbers and the imaginary part to be the imaginary parts, okay, for a complex number. So if I just had something like 2 plus 3i, right, we could go 2 in the real direction, 1, 2, 3 in the imaginary direction, and we would just say, there, that's 2 plus 3i. Okay, but that's not really what I wanted to show you just yet. Okay. What I wanted to show you was that right, we start with 1. Okay, here's 1, 0. This is 1 plus 0i. And we said, okay, 1 times I is I. So I is 1 up, right? This is in the imaginary direction. We're going to go move 1 up. This is 0 plus I. Okay. And then if we multiply by I again, I squared was equal to -1. So it's -1. It's the real numbers, but it's in the negative direction. So this is -1 plus 0i, or -1, 0. Okay, and then multiply by I again. -1 times I is going to be I cubed. Okay, but it's -I. It's going down one direction. So it's not positive imaginary direction, it's negative imaginary direction. So this is going to be -I, or 0 minus I. So notice every time I multiply, 1 times I gave me I. I times I gave me -1. -1 times I gave me -I. And -I times I gave me back to 1. And this cycle repeats over and over and over and over again. Okay. All right. Now, what if I have 2 imaginary numbers? Okay, but the first 2, like I squared, that's like the one you really need. So Z is the traditional symbol for an imaginary number, so or a complex number rather. So if we say this is 3 plus 2i, and Z2 is equal to say 5 minus I, then Z1 plus Z2, right? This is 3 plus 2i plus 5 minus I. And I'll ask you, if you're in the third grade or the fourth grade, how do you think we should add these up? How would you like to add these up? You're going to say, well, why don't we add the real stuff together and then add the imaginary stuff together? Sounds good to me. That's what you do. Okay. So you know theta is like the x for angles, and x is the x for algebra. Z is the x for complex. Okay. I want z minus z2. Okay, how do I do this? I would say 3 plus 2i minus 5 minus I. So can we do the same thing? Well, if you mean by the same thing that we're going to factor the -1 sign into the complex number here, then yes, that's exactly what you want to do. The same thing. So 3 minus 5 is going to be -2, and 2 plus I is going to be plus 3i. Okay. So there we go with that. What if I want to multiply them? 3 plus 2i, and then 5 minus I. I want to multiply these together. And I hope that every part of your being that still remembers intermediate algebra is saying FOIL them. Okay, that's what you want to do, is you want to FOIL them. So 3 times 5, that's going to be 15. We're going to have a plus 2 times 5 is 10i. Okay, we're going to have a minus 3i, right? 3 times -1. And then we're going to have a minus 2i squared. Okay, 2i squared is a negative sign. Okay, so let's go ahead and simplify this down. We're going to have 15 plus 10i minus 3i. What's I squared? Squared is -1. So minus 2 times -1 is really a plus 2, isn't it? So this is going to be 17 plus 7i. Okay. So you now know how to add, subtract, and multiply complex numbers. Got one more operation. Okay, how do we divide them? So we want Z1 over Z2. 3 plus 2i, 5 minus I. Okay, and for those of you who are jumping up and down saying synthetic division, I'm sorry to disappoint you. We're not doing that. What you're going to do is you're going to multiply by the conjugate. Okay, so we multiply by 1, we just multiply by the conjugate of the denominator and see what happens. So on the top, we end up with 15i, right, 3 times 5, plus 10i, okay, plus 3i plus 2i squared. On the bottom, we have 5 times 5 is 25. We have a minus 5i, that's these two. We have a plus 5i, that's the outers. Okay, and then we have a minus I squared. Okay, so let's go ahead and simplify this down. So you got 15, oh, this is just 15, it's not 15i. Oh, sorry. It's just 15. So we have 15 plus 10i plus 3i. What's 2i squared? I squared is what? It's -1. So we have a minus 2 here. Okay. Then on the bottom, we have 25. Okay. These two cancel out. And again, we have a minus I squared. I squared is -1. So minus a -1 is plus 1. Okay. So we end up with 15 minus 2, that's 13. Okay. This is going to be 13, so plus 13i. Okay, I didn't mean to do this to you. I mean to make it work out this way. They don't always. This is by chance that this ended up this way. And then we have 13 over 26. That's my real part. plus 13 over 26i. That's my imaginary part. So that is 1/2 plus 1/2 I. So why'd you write it that way? Because complex numbers like to be written a plus bi. Okay, so I don't want to write the whole thing as a fraction. It's not wrong, but if you're ever going to work with an electrical engineer, they're going to want to see their complex number look like this. Okay, so if you write it the other way, you're going to make them a little upset. So we're going to be nice, and we're going to make sure that we've written our complex number in order to make sure that there's harmony between the engineering classes. Okay. So there we have for complex numbers. Now, if you, like I said, if you're only using this for like, I just need to get to my homework, I would recommend this is the place to stop. Okay. Now we're going to talk about the derivation of polar, okay, which we'll pick up on as givens for the next video. Okay. So it's going to be a little bit long, so I apologize. But this is going to say, okay, we're going to say e to the x. What's e to the x going to equal? Okay, so I'm going to come over here with Desmos so we can draft, we can say this is y is equal to e to the x. I want e w to the x. Okay, and we'll go with black. Okay, and we'll go with the dotted line. Okay, there we go. Now I want a comparison graph, and I want to say y1 equals, and I will say 1 plus x, okay, plus x squared over 2 factorial. Remember the factorial? It doesn't mean that the 2 is really excited. It means this is 2 times 1, okay, plus x to the 3 over 3 factorial. So that's 3 times 2 times 1. Okay, plus x to the 4 divided by 4 factorial. And I hope you're kind of watching what's going on with the blue graph and what's going on with the black dots graph. Okay, they're getting closer and closer and closer together. Do this. I've never done that before. Let's not do that. Let's do that so it's easier to see. So you'll notice that with every successive term that I'm putting in here, it's getting a little closer. Oops. Okay, it's getting a little closer for every term I put in. Now I could put in an infinite number of terms, okay, and then we'll have our e to the x and this sum be equal exactly. So there's a plus there. Okay, so after a very, very long time of adding more and more and more terms here, my e to the x, what the heck happened? There we go. No. See, Control Z, there we go. Control Z is a wonderful key. Okay, but we're going to get closer and closer and closer to the black dots. Eventually, these are going to be the same. Okay. So, what I'd like to do, well, yeah, let's pause for a moment here. What I'd like to do is instead of putting a e to the x equals 1 plus x squared over 2 plus x3 over 3 factorial plus x4 4 factorial, x5 over 5 factorial. I suspect you get the pattern. Okay, plus dot dot dot. I'd like to put in an e to the minus, or e to the I theta. No minus, just e to the I theta. Okay, and that's going to replace my x. So we're going to get 1 plus I theta to the 1 plus I theta squared over 2 plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the 5 over 5 factorial plus I theta to the 6th over 6 factorial. Okay, now we're going to simplify this a little bit. Okay, this is going to be 1 plus I theta plus, what's I squared? It's negative 1. So it's minus theta squared over 2 factorial. What's I cubed? Well, it's minus I cubed over 3 factorial. What was I to the 4th? That was 1. So that's just going to be say theta to the 4th over 4 factorial. What's I to the 5? That was the same as I. So we're going to have plus I theta to the 5th over 5 factorial. And back to what's I to the 6th? Well, that was negative 1 real. Theta to the 6th over 6 factorial. And then so on. Okay, and what I'm going to do is I'm going to break these apart. I'm going to have the real part and the imaginary part. So we're going to have 1 minus theta squared over 2, skip this one, plus theta to the 4th over 4 factorial, minus theta to the 6th over 6 factorial. Are we seeing a pattern? Theta to the 8th over 8 factorial, minus theta to the 10th over 10 factorial, and so forth. Okay, so it's 1 minus plus minus plus minus plus minus plus, and these are just getting ever increasingly values that are even. For the imaginary part, what's left? You have this, 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 so forth. So what I'm going to do is I'm going to say this is I, okay, and then we're going to have theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so forth. Okay, so I want to show you the next couple of things on Desmos because we're going to make a little substitution here. Okay. So we're going to, this, by the way, a lot of what I'm pulling out here is all out of Calculus 2. So unfortunately, to see the derivation of why these are the same, you're going to have to take Calc 2. Okay, once you get to the end of that, then this will make more sense. So I apologize for the fact that I'm just asking you to take this on faith from me, but please take this on faith from me. Okay, so I'm going to say this is y is equal to cosine of x. Okay, let's go ahead and get rid of this. I can even make it closer. I can just say theta. Okay. And then what we're going to do is we're going to go with, let's say, 1 minus theta squared over 2. Okay, this is y equals, sorry. Okay. We'll move this up and no. Okay. And then plus theta to the 4th over 4 factorial. Okay. Minus theta to the 6th over 6 factorial. Okay, and again, what you see is every point I put in here, right, it gets closer. 8 factorial. So every point I put in here extends this little spot out where the blue and the purple, the black and the purple match up closer and closer and closer and extends this out. So just like in the previous one, okay, just in the previous one, if we extend this out infinity to infinity, then these two functions are actually going to match. Okay. So this even part, this is effectively equal to cosine theta. Okay. Now, if we look at the odd part, we look at this second part here. Okay. I'll bet you know it's coming. Okay, we're going to put a y is equal to a sine x, or sine theta. Okay. And then y1 is going to be theta. Okay. Minus theta cubed over 3 factorial okay, plus theta to the 5th, oops, over 5 factorial. Okay, you see how it's getting closer? Theta to the 7th over 7 factorial. And again, the more terms we pick on this is the closer that this piece here is going to match the red. The blue one is going to match the red one. Okay, and again, plus dot dot dot, we're going to see that this series, this summation here, is equal to the sine of theta. Okay, and it's not going to be equal there until this goes off to infinity, but I don't think you want to watch me type that in, so I'm going to have to take our word for it. But you could extend this, you know, if you're bored someday and you want to say, I'll bet I could do it, you could extend this out for as many terms as you want. For every term you extend it out, this is going to get a little bit bigger and they're going to match a little bit better. Okay. So we're going to go back here. We're going to say, this is equal to the sine of theta. But what did I put here? I put an I. All right. So to boil this down, remember where this whole series came from, right? It came from e to the I theta. So we're going to have e to the I theta is equal to the cosine of theta, that's the real part, plus I sine theta, right? And this is the polar form, okay, of a complex number. Okay, and that's what we're going to be using. So the trig comes back into it. We can do more trig. Okay, we're also going to show you another thing. Okay, and this will be the last thing. Okay, now after this, we'll go back. We'll do the next section, and there will be far less witchcraft going on here. Okay, we're going to say that e to the I theta is equal to e to the I theta over 2 plus e to the I theta over 2. All right. And then what I'm going to do is I'm going to say I'd like to add e to the negative I theta over 2 and subtract e to the negative I theta over 2. What did I add? If I add these two together, we get back to 0. So all I did was add 0. Okay, so I'm going to shuffle them. I'm going to say this is e to the I theta over 2 plus e to the negative I theta over 2. Okay, and then we're just going to hold this off. We're going to say this is e to the I theta over 2. That's this one. Okay, minus e to the negative I theta over 2. So I just shuffled it. I kept the positive one over here, put the negative one with this one. Okay. Now I'm going to do one more thing here. I'm going to say that this is e to the I theta over 2. That's this one. And we're going to say this is I over I. So I over I is 1. Okay. Minus e to the negative I theta over 2 times I over I. Okay. So we're going to have I e to the I theta minus e to the negative I theta all over 2I, right? Because that's our common denominator. So I'll cancel them. They won't. So what I want to do is I want to come back up here and I want to say, remember that e to the I theta, right, is equal to cosine theta plus I sine theta. I also want to put up that e to the I theta is equal to e to the I theta plus e to the negative I theta over 2 plus this I e to the I theta minus e to the minus I theta over 2I. And what I want to do now is I want to say, e to the I theta equals a real part, cosine theta, plus an imaginary part, I sine theta. Or e to the I theta is equal to a real part, e to the I theta plus e to the negative I theta all over 2, plus an imaginary part, e to the I theta minus e to the negative I theta all over 2I. I'll bet we can equate these and say that cosine is equal to e to the I theta plus e to the negative I theta all over 2. And I sine theta is equal to I, and then times this stuff. This is e to the I theta minus e to the negative I theta all over 2I. So we're not going to worry about the i's out here so much. We're just going to say, look at that. The sine is equal to that. So that's what I wanted to show you to kind of get an idea of why we are going to be talking about e to the I theta is equal to cosine theta plus I sine theta. But there's times where we're going to go and revert to this as well. Okay, and again, Calc 2 unlocks a lot of these mysteries, but you know, to be honest, I missed some of this in my education. I was taking some 400 level class about mathematics for engineers, and they dropped this on me, and I was like, oh, whoa, this made so many of my problems so much easier. Like, yeah, would have been nice to learn that earlier, huh? Yeah, it would have been. So here we go. We're learning it early, so that when this comes around, you'll be able to take care of it. And I'll show you a couple of other things later on with this. Okay. So I'm going to leave it there. We're going to work the next thing on some homework. So for those of you who skip past this, you can come back in. I know you can't hear me. Okay. So we'll meet in the next video. All right. Thank you.